Let's just start off by defining our terms. So first of all, it's a base operating system that we use for running containers. And because containers contain all of the dependencies that they need, the actual base OS can be really minimal. It just has what you need to run containers, like a container runtime. Typically, it has a secure, immutable file system. So the file system itself is read-only. It can't be changed at runtime. That has security implications. It also has, obviously, manageability implications. You know exactly what the OS partition has on it. We follow a declarative provisioning model. So in just a similar way to how with Kubernetes, you define your YAML file, that's the declarative configuration that you want to have, so end deployments or whatever, you define a configuration file for your operating system. The machines then stand themselves up, read that configuration file, and run just how you want them to. And we have an automated update system. So a container Linux-based system is typically going to be checking for updates and applying those automatically without you as a user having to think about the schedule for that. You can define policies for how they're applied. You can coordinate it with Kubernetes so that nodes are cordoned and drained and all of that before an update is applied. But the idea is essentially, as Alex Polvi, who was the CEO of CoreOS, that came up with this concept, called it, is self-driving Linux. You just define the destination, sit back, and it takes you where you want to go. And CoreOS was the original container Linux and launched just over 10 years ago. And here's, in fact, one of the reviews at the time when it came out. So people immediately saw the potential for this model to massively simplify management of large, at-scale production deployments. And so people saw that this was where things were going to go, whether it was actually CoreOS container Linux or some other variants and derivatives, but it was clear that was the direction for people who wanted to deploy containers securely and in a way they could easily manage at scale. And in fact, that's how it turned out. So while CoreOS was the first, it was a whole series of derivative and inspired by distributions that came out following CoreOS. So Red Hat was probably the first. They liked the idea so much, they came up with their own project, Atomic Host, and then they liked it so much that they acquired CoreOS and integrated the original CoreOS with Atomic and created this thing called Red Hat CoreOS. But that's slightly different from the original one. So then our team that Thilo and I are part of were working at Kinvolk at the time, a Berlin-based startup, and we did a fork of CoreOS Container Linux, and, which was called Flatcar, and continued that. And in fact, that's recently just been submitted to and accepted into the Cloud Native Computing Foundation. So you now have a community-based Linux based on these concepts of container Linux that were defined 10 years ago now. So this is all looking back a little bit. We'll get onto the future in a minute, but I just wanted to kind of define some of the ground terms, but also point out that a lot of what we think of as the fundamental principles and technologies that define and have defined the cloud-native revolution over the last 10 years actually came out of CoreOS and out of container Linux. So etcd, which you think of as the heart of Kubernetes, how we distribute state information around a cluster, that was originally a component of CoreOS container Linux. OCI, Open Containers, the standards for how containers got implemented across the industry, came out of the original CoreOS work, building alternate runtimes and pushing for an open standard. How we think of security and updates in a containerized world, the whole DevOps model really kind of came of age with container Linux. So I think there's a strong argument for the OS being a driver for a lot of the innovation that we see, and it's certainly a foundation for the innovation that we see. So with that in mind, let's think about what does the next 10 years look like? If that's what has happened over the last 10 years, where do we go from here? And I think there's a key point that we should make here when we think about the operating system and innovation and how this evolves, because particularly when you think about container workloads, there's a well-defined abstracted interface between the container, the containerized application, and the OS. And as long as we maintain that contract between the underlying OS and the container, we can do a lot underneath the covers in terms of the architecture of how it's built, alternative ways of deploying it, how we implement security, a whole lot of things we can do under the covers and innovate, which don't change the operational model. And therefore, if there's a takeaway from today, I would say it's just keep an eye out on this OS layer, because even though you may not think about it every day, and it may feel like it's a commodity and not really changing, there is a lot of innovation happening there as well. So let's think about the next decade, and let's talk about some of the things that we're doing here. The first piece is how we're evolving the concept of distribution. And I apologize. Are you taking this piece over?
No. I absolutely could.
No. I think we're going to change it in a minute. So so how we have evolved the concept of distribution. The original container Linux concept was we'll define a very minimal distro, and we'll keep it very, very small because everything's in containers. And that worked well for a long time, but as maintainers of those distros, one of the things that we see is we get a lot of requests for additional packages. Oh, can you add this one additional container runtime? Can you add this one additional thing here? And as we do that, if we were to accept all of those, we would move away from that minimal curated model. So we need to move towards a model where it's more composable, where users can decide which packages they want to include and exclude. Unfortunately, there's a technology that's fairly recently come into the systemd world, which is obviously part of the distro, called system extensions, or sysexts. And this allows us to actually layer additional packages and files into the operating system without it being package managed, right? Because that's the old world of general purpose operating systems. So we still want it to be part of the immutable file system, but we want users to be able to actually compose these files. So a sysext is nothing more than an overlay file system that you're going to put into the USR or opt directory. And it's packaged up as a disk image, and it's loaded at boot time by this systemd sysext runtime. So that's a very, very simple in concept. It's actually very similar to containers in the way that containers are overlay file systems with a bunch of other things as well. We've actually used this probably over the last 12 months or so, if you've been keeping an eye on Flatcar releases. Again, as a user, you won't have noticed a whole lot of change, but under the covers, we've adopted system extensions as a way of re-architecting the operating system. So there were a number of things that CoreOS Container Linux had that Flatcar inherited, which were kind of kludges, which we've re-architected. So how we implement custom container runtimes, how we do OEM-specific partitions, for example, for AWS or Azure or VMware, and more recently, how we've integrated into Cluster API. So these have all moved to be implemented as system extensions. Now, before we move on and talk about and show how we actually use these in practice, I need to explain a little bit about how Flatcar is provisioned, because it does have this declarative model, right? So, as a user, you configure a set of configuration options. I mean, there are same defaults, so you don't actually have to configure a lot, but things that you want to specify. So, for example, which sysexts I want to combine in this runtime. I create that in a YAML file. I provision that to the OS at provisioning time. It's converted into JSON. It's passed in via, for example, iPXE. And then on first boot, it's going to pick up this sysexts, apply them, and then also apply updates. So what this looks like, the config file that you use, as you can see, it's very short here. Basically, we just provide a path to the sysext, that's that raw file, and tell it and tell systemd where to put that sysext in our directory hierarchy. And hard false being this is going to be putting it in there as a soft link. Well, how do we apply updates in this model? So we've got this sysext applied into our OS. First of all, there are actually different kinds of sysexts. So there are ones where it's completely independent of the system, of the actual underlying OS. There's no dependencies where it's relying on the OS to have certain files in certain places. And that's the easiest case. Systemd comes with a sysupdate function, which basically does a simple semver-based check. Is there a newer version over HTTPS to a server sitting somewhere, and pulls down an update if there is. If you've got something that's a bit more dependent, where you might need to actually have things done in sync with the OS, then you may need to coordinate with the actual OS updates. So you might need to go to a more recent OS version in order to get that sysexts updated. And we've actually extended the Flatcar update server with understanding of sysexts as well, so you can pull down the updates along with the updates to the OS. And then the last and kind of most OS-dependent one is where the sysext itself is actually baked into the OS image, and there you're just going to pick it up with a new OS image in the same way that you would update Flatcar on a normal basis.
So I think we need to be clear that for you folks, for the users, the OS-independent sysexts are the most interesting ones. For us, it's the other two. So that level of extensibility to Flatcar that we provide and we demo, that is independent sysext, which you can update at your own pace. The other stuff, it's basically on us.
Yeah. Now, we also need to update these sysexts once they're in there. How that looks is essentially within that YAML, there's an extra little bit we're going to put in, one of which is a path to a config file which defines what type of update model you're going to use for that sysext. And then you need to also create a systemd service called the sysupdate, which just runs on a timer and checks for new updates. So with that, I'm going to hand over to Thilo to show you this in practice.
Yeah, so we're on a Flatcar node here. This has not been instrumentalized or customized. This is just a plain Flatcar node booted locally on that machine in the QEMU provider. And I'm just going to quickly show you what Andy already mentioned, that we have system-dependent sysexts, which we ship, and those are merged. Like nowadays, we ship containerd and Docker as sysexts because turns out the interest goes both ways. So folks are not just interested in adding stuff to Flatcar, they're also interested in removing stuff they don't really need in their deployments. So containerd and Docker nowadays are shipped as sysexts. We see those three sysexts. And then I need to show you that in USR bin, there is nothing that starts with QU, and why I'm showing you that, it'll be clear in a moment. I'm going to shut down this virtual machine. And I started this in snapshot mode, which allows me to basically throw away all of the state when I power off the machine. And now I'm going to take a quick look with you into our demo YAML file. It's basically what Andy described, with a few additions in order to make my local Flatcar instance pull the Kubernetes sysexts from my local web server instead of the bakery, and the reason for that is the conference Wi-Fi. So this is going to work, but otherwise it's practically the same configuration. I also disable the systemd sysupdate timer because I want to demo it to you, and there is no demoing if this just happens in the background, and then stuff already happened while I was talking. So now we have the sysext merged, and I have Kubernetes running in a plain configuration on a single node, like not much to see here. I can show you the binaries in USR bin, and just as Andy said, this is being merged transparently into the root file system. And if I now do my little list operation here, then you'll see that we have 4 sysexts merged, and one of them is Kubernetes. Now, the soft link magic. If you look at this file, oops. So that's the Kubernetes sysext that systemd is aware of. You see, it's just a symlink into the place where we deploy the actual sysext, and that is where systemd sysupdate comes in, because sysupdate, which I'll start in a second, will recognize this. It understands semvers, right? So it understands the last part of this file. It will also be configured to check my local web server for updates, and there happen to be updates. So I will now system cuddle the sysupdate service. And normally this would be done by the sysupdate timer, which would, in intervals, basically check, and you just control the intervals that your node checks for updates via the timer configuration. Now, sysupdate will have detected an update, and something I didn't show you, so where we put the actual extensions in opt extensions Kubernetes, there was, trust me, there was one file, and now there are two. Because this update basically just pulled a new file, but something that I did show you and that did change is the soft link. So now the symlink goes to 134, and if I run kubelet version, what version do you think you're going to see? Right, it's the old version. And that's because the update was only staged, is not activated yet. I could refresh the local sysexts configuration, basically just reloading the config. But you could have workloads running, so the safe method to activate that is actually, one thing I need to show you before rebooting. This will be important later. So I just take a look at the run directory, and in the run directory, we see a file that looks a bit unusual. That's called reboot required. This is our interface to the Kubernetes world later on. Systemd sysupdate has created this file when it detected there was a new version, and when it installed the new version. All right, now I'm gonna reboot. So this is basically how we tell Kubernetes operators that a node would require a refresh, and then you could do from the operator side, you could coordinate those refreshes. So. We now have, I always do this wrong. It's not kubectl because kubectl doesn't know version. It's kubelet. We updated, in place updated Kubernetes. Oh, you want me to continue? Right, yeah. This is the bakery. This is basically where you would usually pull your Kubernetes sysexts from. And we actually gained some traction with the community here. So we added like a full-blown Docker and multiple versions, so you can pick your own Docker version. We added Docker Compose, which we don't regularly ship with Flatcar, so you can compose that into your node. And we're actually using this for some of the Flatcar apps that we're working on. And users basically picked this up very well. So Wasm Cloud, Wasm-time was added by a third party, and basically everything that follows was not added by us. So we have Cryo, K3s, recently even Olama. And if you've been in the previous talk, that was just about this LLM. So that's basically your go-to place. You can even, fork this, use your own automation around it, and then basically provide your own sysexts, which a lot of people are doing. Yeah, taking this, we actually applied the sysexts principle and the in-place updates to something that also came with a little bit of a legacy, and that was Cluster API. So when we started with the Cluster API project, adding Flatcar support, we basically stumbled over this image builder project, which would create user-customized file system images of whole distros with Kubernetes bundled in, and you would need to build those images. You would need to, certify those images, make sure everything's up to date. You would need to host those images yourself. There's no official image registry for Cluster API for none of the providers that I'm aware of. And there's like a ton of maintenance overhead involved in that. Also, you couldn't in-place update Kubernetes and the operating system, because anything concerning updating a node in place was kind of a nightmare, because everything was meshed together in the image builder step. Now, we just took our experience of the sysexts and applied it in a second wave of support to Cluster API providers. We basically ship in some of the proof of concept implementations and in the OpenStack production implementation, Kubernetes as a sysext, not merged together in an image. So you can use stock operating system images that are already available in all of the clouds, that are updated by the operating system vendor, so you don't need to host your own operating system images. Put Kubernetes on top at provisioning time, and that would focus you as the user or the operator on maintaining the Kubernetes sysexts and controlling those updates instead of, more or less hosting your own distro images. It also allows for in-place updates in cluster API. So if you're using sysext composition on Flatcar in cluster API, you can in-place update nodes with the Kubernetes version without deleting the node. And that's my second demo. I have a very small OpenStack cluster API cluster here. You see the control plane is just a local kind cluster, and I only need one node that runs the cluster API controller. And I have 3 worker nodes on my worker cluster on OpenStack. One is the control plane, and the others are worker nodes. So if I check the control plane node, which is this IP address, and then system d sysext list. Look at the list of sysexts. We see Kubernetes is merged. If I check the place that we had earlier, then you see that apparently on this node, and by default on all of my cluster API worker nodes, system the sysupdate timer is active, is running, and in this case already fetched the update. And it is asking kindly for a reboot. So we have the reboot required file here. Now the thing you don't want to do when you're operating cluster API clusters is you don't want to SSH into the nodes and reboot them, right? You want to have automation that does that reliably and safely. And for this, we're just going to use QD. So I can now kubectl apply. KC worker is just a wrapper around kubectl with the right kube config. QD, and so it's going to put that on my worker cluster, and I can, it usually takes about 30 seconds to start understanding that there's a reboot needed. So we're going to start here, taking a look, and as soon as the first node has updated, we're going to continue the presentation and later on take a look again. And you will basically see that node by node, the status will go into scheduling disabled, the node will reboot, and then the Kubernetes version will have updated. It's about usually 30 seconds, and then QD picks it up. Except when you demo, then it takes longer.
It works straight away when we practiced. There we go.
Yay, the first node is being rebooted. It's a worker node, and that's good. In some of the demos, so I didn't really dive deep into configuring QD and which nodes should be rebooted first. There's numerous options. QD is awesome. And in some cases, when I practiced that, it was the control plane, and then you run get nodes and you don't get a response because your control plane is currently rebooting. But in this case, we're going to see the first node has updated to 134, and the other nodes will follow. So this one will be uncordoned soon, so pods can basically repopulate. But I think starting here, it's kind of boring to watch this, so let's go back.
That's cool, Thilo. So let's talk about the third topic for the next decade. And really, this is one that I think a lot of us spend a lot of time thinking about. And it's something that's changed a lot versus 10 years ago when CoreOS first came up with the container Linux concept. Back then, it was enough to be secure to just have updates automated, basically. That was kind of the security story, was if you're up to date with the latest packages as we publish them, you're going to be secure. Today, though, we see a whole load of new threats. Right? It's not just that CVEs are being discovered at a faster rate. It's also the types of attacks that we're seeing are changing, and the types of attackers are changing as well. So this means that we really have to think very carefully about what that means for the whole infrastructure, from the hardware through to the applications.
Yeah. And this is like a whole chain that needs to build up on top of each other. And it starts with, as a distribution, what sources do you consume? How do you check that what you're actually consuming in terms of source code is what you would expect to consume? Like with any given package version, did you get the source code that you were expecting? You need this verifiable, documented, accessible, because your compliance department will want to know what's running on your clusters. And ideally, you have a layer on top that gives you automated alerting if something is in your cluster, so you can take countermeasures. It continues with the runtime, so it doesn't really help a lot if you have everything documented and your sources checked, and then people can basically break into your nodes, fudge something with the runtime, and then silently leave, so you're running their workloads instead of yours. So you need to make sure that whatever bootloader, operating system, and application stack you run is verified and measured, and up to a large degree tamper-proof. So as soon as something's tampered with, things should just break, and you can go and investigate. It is very important to empower the user and not, only rely on a cloud infrastructure to do that for you. And this includes concepts like having your own key management and signing infrastructure, so you can vet and sign basically the applications that you need. And this leads into confidential computing. And right now, it's more for the big players, for the big cloud companies, but I think for the individual operators, there's a lot of value of what's coming here. Yeah. And then when you pull updates for either your applications or the operating system, and you don't validate those, then, well, that's the third kind of angle that nodes can be taken over. So in Container Linux case, right now, and even more in the future, you shouldn't trust sources just because these are the sources that you've once defined. You need to look at everything that's coming from anywhere with the same level of scrutiny. So this includes tamper protection against man-in-the-middle attacks. And our challenge here, and something that we're trying to tackle, to start tackling with sysexts, is even then you need to allow multiple vendors to basically sign stuff and update stuff. In our example, that would be us providing the operating system and intermediate vendor providing base level sysexts, and you providing the application. So it must be possible for all three to basically have the same level of scrutiny.
Yeah, so security is super important, and probably the thing that's going to take most investment from the team to get right, I think, over the next few years. The other big thing that's changing is the kinds of workloads that we're running and how we run them and where we run them is also going to evolve, right? So the operating system is going to have to evolve in response to the kind of innovations that are happening both above and below it in terms of hardware and the workloads. And the first thing we've seen there is CPU architectures. So we've introduced ARM support as at GA level fairly recently. And we've had some folks come into the team that have a lot of passion and excitement about what's happening with RISC-V. So there are RISC-V enthusiasts working on that as well. So I'm excited to see where that kind of goes. The other thing is, it's not just about containers anymore. We're seeing a big wave around WebAssembly or Wasm, and folks want an OS that's appropriate for running WebAssembly workers on. Now, sometimes that will be within the context of Kubernetes, and sometimes it won't. Now, for those who don't know what WebAssembly is, there's a few points here. Basically, very, very lightweight. Think of it almost as kind of a next generation beyond containers in terms of how you can package very, very small pieces of code in a lightweight way, running in a sandboxed environment. So very good for kind of edge applications, CDN-based applications, things like that. And it needs a runtime. Just like containers have a runtime, Wasm has a runtime. There are because this is so early, there's a whole load of technologies around Wasm, a lot of different runtimes and things like that. I've highlighted a couple here because they are specifically in that sysexts bakery. So if you want to try them with Flatcar, all you have to do is to configure that sysext and say, I want to run Flatcar with that sysext. Which leads to the question, well, I could basically make a Wasm Linux, right? We had a container Linux. We could also have a Wasm Linux. And sure, you can, because, as Thilo mentioned, the ContainerD and Docker are just sysexts as well. You can turn them off, right? You can pull them out, just add in the Wasm runtime, and now I've got a whole stack which is just what I need to run Wasm modules. So this is pretty exciting for a lot of the Wasm crowd. And Thilo's just going to show us how this looks.
Yeah.
You can probably see that the nodes have updated as well.
Right, I can actually get the status here, and we have fully updated. All right, so I need to power down the node to redeploy it. This is the standalone thing on my machine again. So this is a super simple Wasm deployment where I run Wasm Cloud on a virtual machine. It's very, very straightforward. It's pulling from my local machine again, but you would usually point it to the bakery. You can have the same self-updating advantages there. I did not do that for the demo, but it's very easy to add. So if we start, oops, hotkeys work different on Mac. If we start this with this configuration now, it'll do just that. It'll boot, it'll merge the Wasm runtime. During booting, that's composable. It took 5 seconds to come up, and now I have Wasm Cloud available. And even more, what Andy said, I can disable all of the other sysexts. So what we don't have available on this machine, because it only needs to run Wasm workloads, is Docker. There's no Docker. There's no ContainerD. Nothing. It's all gone because we're focusing on Wasm with this workload.
Awesome. And shout out to Jonas Bergius for having contributed that sysext into the bakery.
Oh, yeah.
So that's the key themes that we see right now. And I guess if there was one takeaway from this talk, it's the OS layer isn't boring. There's innovation happening there. It's enabling the ongoing evolution of what we call cloud native, and really broken down into kind of these 4 areas. So how we're implementing composable architecture, how we evolve the thinking of cluster API and how we manage multi-cluster kind of scenarios, addressing security, and addressing the expanding scope of next generation workloads and architectures. So with that, we'll wrap up and take any questions. Thank you. Oh.
Thank you so much for this session. We have a couple of questions. So let's start by this one. Do you think bootc, bootable container images on bare metal, will be relevant in the future? What Flatcar's response to this?
I would say it's kind of supplementary of what we're doing. The problem that we're actually solving is to enable the actual booting, right? So for bare metal or for like basically any environment, public or private clouds, you need the respective tested and hardened support, particularly if you're thinking about measured boot and secure boot. But even if it's only just vendor support of the respective clouds, and that is what we're focusing on, basically delivering that, be it as a more or less bootable container or as a Wasm workload. So we see ourselves kind of between that.
There's a whole lot of infrastructure that Flatcar brings around updates particularly that you're not going to have with bootable containers.
That's true, yeah. It's less static.
How do you compare the systemd sysexts approach with RPM OS 3? Do you see any major benefits or issue with either one?
The difference is that OS 3 is based on a specific feature of one file system. So you're basically limiting yourself to this. It can be more advanced, particularly in the RPM OS 3 flavor, in that you have more degrees of freedom. We don't really need that on the Flatcar level. We actually like the simplicity of systemd sysexts because it's image-based, immutable, atomically updatable, and rollbacks work as well. So it compares very much to what we're doing with the core operating system. And we think simplicity is good on the operating system layer. But I mean, your mileage may vary. If you need the flexibility, RPM OS 3 is a nice approach.
All right. Can you run Flatcar Linux on bare metal? What about features like network bonding?
Flatcar runs on bare metal. So we have folks using that on bare metal on their private clouds. We support a range of bare metal vendors. You can use AWS bare metal instances. We run on Equinix Metal. It's actually very well supported. And network bonding is basically a configuration detail. So even if the base distro doesn't recognize bonding by default, it's very, very easy to add in your custom ignition configuration. We would be very glad if you detect issues with bonding and you need to add manual configuration to that, if you could contribute back to the upstream project, because then we could support it for all users. But we're not aware of any issues on current platforms that we support.
So basically that means that I can run Flatcar Linux on my RPIs.
It should work, yeah. If it doesn't, drop us a note.
Yeah. Trust me, I'll do. All right, one last and probably a funny one. So what are you saying is by using Flatcar, we will be fine in the next 10 years?
Yeah.
And beyond, hopefully.
And beyond. Flatcar tries to be that thing for you that you just put into a corner of a data center and then forget about it next 10 years because it's self-updating. It tries to never, ever bite you. This contract Andy mentioned at the beginning between your application workload, containerized workload, and the operating system, we very, very much honor it. We understand it as the one thing that we're doing in Flatcar. And so, yes, absolutely.
If I can add one thing, so we are close to have a systemd operating system, kind of.
We like systemd.
Yeah. I would say quite close. There are edge use cases out there that people operate on scale that boot from BIOSes. And BIOS isn't really a thing Leonard likes. So we need to wait until everybody is on UEFI, and then we're pretty close.
Thank you very much. Enough. Oh, yeah, that's it for the fun. Thank you all for joining this session. Thank you too for this great session.